second part of the lecture deals with rate of change and behavior of graphs. What is that? It's important to figure out, at least in average, what happened with the rate of change of a function. The average rate of change, shorthand for that, AROC of a function f of x between the input values x1 and x2 is given by this formula. Change on the output values, right? Change on the output values, f of x2 minus f of x1, difference on output values over the difference on the input values, difference on input values. This is how you compute in average the change, the variation of the function, right? Now, mathematicians use this Greek letter delta as a way to express the difference on the output values. This is delta. And this whole thing is read delta y. This also delta, right? It's a Greek letter, delta x. All right. Now, this has a geometric interpretation. Look, if this is your input value x1, then the output value associated to x1 will be f of x1 here. x2, the output value associated to x2 will be f of x2. Now, suppose that your graph is this, the graph of your function, something like this, okay? Could be any curve, right? But now, the average rate of change is gonna be the slope of the secant line, this secant line. The slope of that secant line, okay, will be your average rate of change. Why, Professor, you say that? Well, because notice this is the delta x, the variation on the input values, and this is the variation on the output values, right? Delta y. Raise over run, the rise over the run gives you the slope, right? So that is why this is, geometrically speaking, equal to the slope of the secant line connecting these 2 points, right? Try to remember this when you do your homework, they will ask you to do that. But let me show you an example, right? How this is computed. Compute the average rate of change of this function between the values x equal 1 and x equal 3. Okay, so you look at the formula, right? Average rate of change is equal to f of x2 minus f of x1 over x2 minus x1, right? Difference on the output values, difference on the input values. Now, what is f of x2? Let's start with this. Well, x2, they are telling me that is the number 3 here, right? 3, so f of 3. So that computed into my formula will be 3 times 3 squared minus 2 times 3, okay? Now, if you compute this in your calculator, let's do it together, right? Look, 3 times 3 squared minus 2 times 3, that gives you this value, 21, right? 21. So let's write out 21 here. Now, what is the second computation? The second computation must be done at x1, but x1 is 1. So the evaluation at 1, 3 times 1 squared minus 2 times 1, right? This is 1, 3, 3 minus 2 times 1, 2, 1, right? You can also check that on your calculator. All right, once you have these two output values associated to these input values, you place them here. F of x2 is 21, f of x1 is 1, over the difference of the input values. The input values, remember, are 3 and 2. So 3 and 1, so 3 minus 1. So 21 minus 1 is going to be 20. 3 minus 1 is 2. 2 into 20 is just 10. 10, right? 10. So 10 is the average rate of change. Came out positive, It means that in average, this function is growing, right? If sometimes when you compute this, it will come out negative. If it comes out negative, it means that in average, the function is decreasing, right? Decreasing over time. All right, so we have this. Now let's do some computations here. Let's start with the number 1. Can you try to do that? Number 1 is easy. Let's start with number 2. This one. Yeah, can you do this here with this function? F of x equal x squared plus 5x. Can you compute the average rate of change? Average rate of change. And I'm going to give you the formula here, f of x2 minus f of x1 over x2 minus x1, variation on the output values divided by variation on the input values. And notice that x2 is the second number. This is x2. x1 is the first number, right? So basically you have to try this. F evaluated at 8 minus f evaluated at 5, right? The evaluations over 8 minus 5, right? Try to compute this and that should take you to the answer. And then I will show you a trick to get it in exact form using our calculator, or if it's exact, if it's just a whole number, write out the whole number. Yeah, very good, very good. Okay, let's do the computations together, right? What will be f of 8? F of 8 will be what we get when we substitute 8 for x, right? Let's find 8. This is 64. This is 40. 104, right? 104. If the numbers are not friendly, guys, use your calculator, right? To play safe, especially in the homework or when you're taking examinations. If the numbers are not easy to work with, use the calculator. 104, right? We got that. Very good. Second evaluation says do the same, but at 5. So at 5, simply change this for 5. Same evaluation. Remember, x is just a placeholder on the function. This gives me 50 now, 50. So the second evaluation, f at 5 was 5 squared plus 5 times 5, 25 plus 25, 50, right? 50, we got a calculator too. So now simply subtract 104, this guy, minus 50, this guy, over a minus 5. 104 minus 50 divided by a minus 5 is equal to what? Take the calculator. 104, you can use this fraction form. 104 minus 50 over a minus 5. 18, right? The quotient 18. So 18 is this. That's the average rate of change. So in average, this function is growing. It's growing, right? Very good, very good. Yeah, that can be done with any function, right? Even with radicals, you should try this at home. I'm going to show you this one. Let's look at that real world problem there. And it's basically the same thing we just did. So suppose that a ball is rolling down a ramp. The distance traveled by the ball is given by the function s of t, where t is the time in seconds after the ball is released. And s of t is measured in feet. For the given function, find the ball's average velocity from t1 to t2. The average velocity means the average rate of change, right? Average rate of change. The ball is falling right? And there is a time 1, time 2, right? So let's say here, this is T1 equal 2 seconds. And later on here, let's say T2 equal 3 seconds, right? They want to know what is the average rate of change between the position and the time, the velocity, right? So let's compute that, right? Average rate of change for this function should be the function, which is the function S of t, right? S of t equal 10t squared. So evaluated at the last input value 3 minus the function evaluated at the first input value 2. That's the variation on the output values divided by the variation on the input values, right? Rate of change. But what is this S of 3? It's just what we get when we replace 3 for t, right? So this will be 10 times 3 squared minus S of 2, 10 times 2 squared, right? Divided by 3 minus 2, 1. Let's compute this in our calculator, right? This is 9 times 1090. This is 40. Yeah, the computations are a little difficult. Divided by 1 is just the same. This comes out to be just 50, right? 50. Yeah, you can check on your calculator. 50, in the end, attach the units, right? Feet per second. In the end, you may attach the units. So 50 feet per second. So this is how it works. This is how you compute the average rate of change. Again, notice came out positive. So it means that this object is gaining distance over time, right? Mm-hmm. Very good, guys, very good. So can you try this and we should move on? Try, this is very similar, but as a practice, I will leave this as a reference, right? So try to do this. Use the calculator, probably you would need it there. Yeah, and I will give you the formula as a hint. Average rate of change for this function will be S evaluated at the last input value, 3.5, minus S evaluated at the first input value, 3, divided by 3.5 minus 3, right? And use this function S of t. S of t here is equal to 11t squared, 11t squared. Yeah, use your calculator or your Desmos scientific calculator. They are available in our website, right? Under the tab Desmos. Or use any scientific calculator of your choice. All right, let's do it together then. This should be 11 times 3.5 squared minus 11, 3 squared, 3 squared, and divided by, this difference is 0.5, right? 0.5. When you compute this in the calculator, guys, when you compute this in the calculator, what do you get? Well, let's do it together, right? Let me show you that this is not really difficult. 11 times 3.5 squared minus 11 times 3 squared. Here, a little shortcut, look, highlight this, slash, and then it just allows you to put the denominator here, right? So 71.5, 71.5, that should be the answer, right? 71.5. In the end, feel free to attach the units. The units were feet per second, right? Feet per second. So therefore, the answer should be this. Very good, number 6. Yeah, excellent. Moving on, guys, moving on. The rest you can do it at home. This uses the formula, right? Twice. You'll be fine. Now let's talk about using the graph to determine where a function is increasing, constant, or decreasing. Increasing, constant, or decreasing. Well, suppose this is your form, your function, and this is its graph, okay? The idea, the method should be to walk along the curve from left to right, to walk along the curve from left to right. How? Well, if you walk along this curve from left to right, notice that basically you are going up, right? Going up here, going up, going up, going up. And this is going to tell us that this is increasing. So your function is increasing up to here, right? Once you reach this point, then basically the output values will not change. They stay constant, right? If you stay constant, then it means that your function will be constant. Continue walking along the graph from left to right, always the agreement from left to right. Now notice that you're going down, right? Going down. The output values are decreasing, going down. This mathematicians call a decreasing trend, decreasing, okay? Very good. Method then, walk along the curve from left to right, to determine if the function is increasing, constant, or decreasing. Now, mathematicians express this by saying that the function is increasing over the interval, look, 1, 3, 1, 3. Constant over the interval 3, 5, 3,5, right? And this particular function is decreasing over the interval 5,9, right? 5,9, right? That's how to express this trend. So I want you to do this here. It's not difficult, guys. It's very straightforward. Try to do the same I did there and figure out which are the intervals where this function is increasing, decreasing, or constant. Can you try it? And the hint, guys, is always right. Walk along this function, the graph of this function to be precise, from left to right, from left to right. Right? Then see the trend, right? What is happening with the output values. And according to that, say, right, it's increasing, decreasing, or constant. Mm-hmm. For now, we have to determine just the trend, right? Later on in calculus, when you take calculus, right, they will show you how to use some tools called derivatives to do this, right? But for now, we just have to identify this, where the graph is decreasing, where the graph is increasing, and where the graph is constant, right? Mm-hmm. And another hint is that this guy is supposed to continue to infinity, right? To infinity, this continues forever. Yeah, so, I see an answer. Yeah, Sarah. You made my day, Sarah. Excellent. Good work. Excellent. Look, notice the graph is decreasing up to here, up to -3, right? -3, very important point, -3. So decreasing here, right? So let's use this color. So all this decreasing, decreasing, decreasing. But then you reach this part constant, right? Constant, constant, constant. And then this part increasing, right? Increasing, increasing. Right? So clearly you have to choose this guy, right? Look, increasing from negative, from 3 to infinity, right? Increasing, because 3 here. Increasing, decreasing from negative infinity to -3, right? Remember, negative infinity lives here. Infinity lives here. And constant from -3 to 3. This piece, right? Very good. Excellent. All right. Now this one you can do it at home is similar. Increase, decreasing, increasing, decreasing, increasing. Right? Let me talk about now. These are easy too. Local minimum and local maximum. Okay, to secure this part. Notice that if you walk along a curve and go from increasing to decreasing, the separation between increasing to decreasing or decreasing to increasing change of trend will determine these special points. These are going to be called local minimum or local maximums. For example, here, walking through, you get to see that first you are increasing, but then you are decreasing here, right? Decreasing. What separates them is a special point. It's called a local maximum in this case, right? Because it's the maximum about around this neighborhood of the input value 3, local max, locally a maximum. You continue walking and you reach this other point, right? This is going to be called now local mean, because locally is a mean. You continue walking and you reach again another peak, local max, and then that's it. These 3 points, the green ones and this red point, are called turning points. Turning points are called turning points. Are turning points, right? Because they separate the trend, right? From increasing to decreasing or decreasing to increasing. Now, mathematicians identify this point as follows. They will say f of x has a local maximum value of, look, they look at the output value for at where it happens, at input value 3, at input value 3. Local minimum value of 1, where it happens, at x equals 6. F of x has a local maximum value of, let's say, this is like 2 more or less, right? 2 is this guy, right? More or less. 2 there. 2 at where it happens, at x equal 8. At x equal 8. Now, f of x has an absolute maximum. What is an absolute maximum? Among the local maximum, the highest is this, right? The highest. So this is also called absolute maximum. So the function will have an absolute maximum value of 4 at x equal 3, right? Now, no absolute minimum, because notice that the function decreases forever here, decreases forever here, right? Yeah, great. Now, local as a word is the same as relative. Minimum is the singular version of this minima, which is the plural version, right? Minimum, singular, minima, plural. Maximum, singular, maxima, plural, okay? Now, I want to show you some examples here. For example, this number 1, they say identify the local maximum, the local minimum, or relative maximum, relative minimum, which is equivalent, right? So quickly you walk along your function from left to right, right, as usual. And you kind of encounter this top of a mountain, let's call it. This has to be a relative maximum, right? Relative max. Then you keep walking from left to right and you achieve this bottom of a valley, right? And this should be your relative mean, right? I say relative because this doesn't have a maximum. Look, this keeps going up, no maximum, absolutely, right? And this keeps going down. So relative max, relative mean. When you identify the coordinate of these points, then you will see that the answer here is this one, right? Maximum at 0,1 here, minimum locally at 2,-3 here. This one you can do it at home. Similar. This one talks about turning points. So let's talk about this a little bit. I will do the first one. I will let you do probably the next. Locate relative maximum and relative minimum points on the graph. State whether each relative extremum point is a turning point. Okay. First of all, right, we said that the bottom of the valleys or the top of the mountains, right, are turning points. They're all turning points, right? Because they separate the trend from decreasing to increasing or increasing to decreasing, right? So these 3 are all turning points, first of all. Now, second, we can say the following, right? Where is the local maximum? Where is the local minimum? Notice that this one is clearly a local max. Locally, no, sorry, local mean. Locally is a minimum, right? Locally is a minimum, local mean. And clearly this one is a local max or relative max, local max. This one, bottom of a valley, right? Local mean. Top of the mountain is local max, right? Local mean. Very good. All right. So now when you identify this with the choices, be careful there. You will see that this corresponds to the first one. Negative 2,4, which is here, right? Negative 2,4 is a relative maximum. And turning point, right? Because they're all turning points. Negative 4,1, which is here, negative 4,1, and 1, negative 1 is a relative minima, points and turning points, right? Are relative minima. Remember, minima is the plural of minimum. So they are relative minima, points and turning points, right? Very good. Can you try this to finish up? They're easy, guys. You just have to follow. Figure this out. As a hint, I'm going to mark the top of the mountains with blue and the bottom of the valleys with red. It's an important point, right? Remember the hint is, or better said, the strategy, right? Is walk along the curve or trace it from left to right, and then you will be able to identify the top of the mountains and the bottom of the valleys, right? So walk along this from left to right. The separation between trends, right, from increasing to decreasing or decreasing to increasing, determine these special points, right? Called relative extremum. Relative extrema, if you want to say this in plural version, right? Yeah, maybe I should write here, top of mountain. Yeah, it's a way to remember this special point, right? Top. For these peaks, right? And for this type of points, bottom of valley. This is kind of a mnemonic device that will allow us to figure this out, to remember it, right? Top of mountain, right? Top of mountain, the blue points, bottom of valleys, the red points, and they should determine the relative maximum, relative minimum, right? Okay, guys, let's do this together so we can finish this. Notice that this guy should be a relative maximum, right? Relative max. Because locally around this input value -2 is a maximum. This one, relative or local mean, right? Relative mean or local mean. All right. Relative maximum is the ones in blue, relative minimum is the ones in red. So we gotta say that -2,3, 1,2, and 4 are relative max, right? And 0,0, this one at the bottom, together with 2, together with 2, -2 are relative minimum, right? And all of them, the blue points and the red points, they're all together. They're all, there's a turning points, right? Yeah. So the answer should be this, guys. Look, -2,3, 1,2, 4,4 are relative maxima. Remember, maxima is the plural for maximum, right? That's what they say, are relative maxima points and turning point, right? Yeah, they are all turning points. 0,0, 2, -2 are relative minima, right? Each of them is a relative minimum. Points and also turning points, right? Yeah, they are all turning points. Okay. Okay, guys, I think we should stop here. Let's just